So today it is my intention to do a practical application. So the lecture of today deals with a practical application about wave propagation. So what we have to do is to make a script, a Python script, able to propagate a wave with given parameters from a point located offshore up to a point located onshore. So just to synthesize the problem, we have again our standard sketch. So this is a point located offshore where we know the wave height, the wave period that we know does not change during the propagation, and also the direction of the wave. So in this point we have the angle of propagation with respect the bathymetric lines. So these dashed lines represent the bathymetric lines. So along these lines the water depth is constant, and somewhere here we have the shoreline. So this is the land and this is the sea. Now the problem is to compute the wave parameter in a point located close to the shore, where the unknown parameters are the wave height, HP, the wave period, that of course is the same of offshore, and the wave angle beta p. Of course this is beta O. And then here we have another direction, that is beta p, that is different in general from this one. And then we need to apply the results that we obtain within the frame of linear theory of waves. Then we know that the wave height at point P can be written as the wave height at the point located offshore times the shoring coefficient times the refraction coefficient, and the shoring coefficient is equal to the square root of the group celerity at the point located offshore over the group celerity at the point located close to the shore. Now the group celerity in general, so both offshore and inshore, is equal to the wave celerity over 2 times 1 plus 2kh over hyperbolic sine of 2kh, where chi, or better c, is equal to omega over k, where omega is equal to 2 pi over t, and k comes from the resolution of the relation of the dispersion relationship, that is omega squared is equal to g, the gravity acceleration, k, hyperbolic tangent of kh. Then we need to compute k to compute omega, or better, to compute omega, to compute k, to compute c, to compute cg, and then to compute ks. The refraction coefficient is equal to the square root of the cosine of the angle of propagation at the point located offshore over the cosine of the direction at the point located inshore. Now, the angle at the point located offshore is given, whilst the angle at the point located inshore is not. Then we need to apply the Snell law, for which the ratio of the wave celerity, that is again this one, over the sine of the wave direction must be constant during the propagation. Pay attention that this is true only for rectilinear and parallel bathymetric configuration, that is the configuration that we are dealing with. Then, in general, as usual, we need to define the flowchart of our script. Then, first of all, we need to start, of course, and after some computations, we need to end. As you know, a flowchart must be designed with a starting point and an ending point. So we need to start somewhere and we must end somewhere else. Then, first of all, we need to get the value of HO, the wave period, and the wave direction at the offshore location. So this is a kind of parameter acquisition. Then we need to perform some computation. First of all, we compute omega, 2 pi over t. And this is the second operation. Then we need to solve the dispersion relationship to get k. Then we compute the wave celerity in O. We can get here O. Then we get the wave celerity that is equal to omega over ko. So this is the wave number at the point located offshore. Then we need to solve again the dispersion relationship in order to get the value of k at the point located inshore, in order to compute the celerity at the point located inshore, that again is equal to the same omega, as the wave period does not change, whilst the wave number changes. Indeed, the water depth is different. Indeed, I forgot, here we need also to get HO and HP. Then we need to compute the group celerity in O and the group celerity in P. And then we compute Ks, that is equal to the group celerity in O, over the group celerity at the point P. And then we have computed Ks. sorry, I delete this one and I put this one here. And then we need to compute the refraction coefficient. So we can solve Snell law in order to get the wave direction at the point P. Then we can compute the refraction coefficient, Kr, and then we can compute HP equal to HO times Ks, Kr. And then we have finished. So we need to write a kind of script, actually a script, able to apply to solve the problem of the wave propagation from the point located onshore up to a point located inshore. Then we simply go here, we make a new script that we can call wave propagation. We change the extension to pi, and then we open with Visual Studio Code and we try to translate the flowchart in a script. So this is the problem. I increase the font size. As usual, description of the script. So when I use an hashtag, we can put into the script some comments, more or less. Then here we can write these scripts, compute the wave parameters at the point P if they are given at a point O. Then we import the modules, or if you want, packages. As usual, we need to import the module that allow us to perform some computations. We import the module that allow us to make some plot, and also we import a function that allow us to solve nonlinear equation. In this case, we need to solve the dispersion relationship, so we need this function fsolve. Indeed, if I come here, this is our presentation in which we brought some useful information, and as you remember, if you remember, we used fsolve, just for example, to solve the normal flow equation, the critical state equation, the standard method. We implemented the standard method to compute the free surface profiles and so on. So we don't use any new functions within Python, but we use all the functions that we have already used in the past. Then we write some parameters, and the parameters are the wave height offshore. We can write just for now wave height at point O. Just for example, 1 meter. This is expressed in meter. The wave period. Actually, the wave period is indicated by a T without the pedis O, because the wave period is the same both at the point located offshore and at the point located inshore. So we don't need to use any any pedis. In this case, the period is measured in seconds, and this is wave period at both points O and P. Also, we need to define the wave direction at the location at offshore, just for example. Then we use also the pedis O, and then we can write wave direction at point O. Just for now, we leave beta O equal to 0, and then we can go here. We need to define also the water depth at the point located offshore, HO, but also the water depth at the point located inshore. So we can write HO is equal, just for example, 100 meters, water depth at the point O, and HP is equal, just for example, 5 meters, water depth at the point P. Okay, so these are the parameters. So we have done this first part. Then we need to compute omega. Some computations. Omega is equal to 2 times pi over t. So we have done also this one. Then we need to solve the dispersion relationship. The dispersion relationship, we can write here, is omega squared is equal to gravity acceleration k hyperbolic tangent of kh. Actually, any numerical model numerical method is aimed to solve a function, nonlinear function, written in this form. Then the dispersion relationship should be written in this way: kh is equal to 0. Actually, x is our unknown, so we can think to write the equation in this way, equal to 0. So this is the function that we need to solve. If you remember, perhaps you don't remember this one, the function that we use is this one, So we need to use this function of Python, actually of the module SciPy, and we need to define the function that we need to solve and a guess solution. So first of all, we need to define the function. So we can come back to to our script, and we can define here the definition of the dispersion relationship. And if you remember, a function can be defined with the keyword def. Then we need to write the name of the function, disp rel, and the argument of the function. As you can guess here, the function are omega, h, and of course the unknown x. So we have three parameters. The first one is of course the solution that we want to get, x, that is actually k. Then we need to give also the value of omega, but also the value of h. So we can write here x, omega, and h. And this function should return the value of this difference, that if it is of this difference, sorry, if this difference is equal to 0, the x value is the solution. If it is small, the x value is the approximate solution. If this difference is very different from 0, x is not the solution of this function. So we need to return the value of this difference. So the difference of omega squared minus this term. So we need simply write omega times omega minus the gravitational acceleration times the hyperbolic tangent of k, that is x, sorry, here we have also k, that is x called here, times h. So we can use this function by giving the value of x, the value of omega, and the value of h. Then all the terms here are known, and then this function can return this difference. If this difference is almost equal to 0, then the x value is the solution. Now we can write k is equal to f solve. Here we need, as you can read here, we need to give to the function the name of the function to solve, the value of the guess solution, and arguments other than the unknown. Indeed, this is the unknown and this is parameters. So we can pass to this function also omega and h. So here we need to write this rel, the name of the function. Then the initial value, so the guess solution, we can write here guess, and then the other arguments between brackets. And the other arguments is omega and h. If we want to solve the dispersion relationship at point O, we need to write the value of omega, that is the same of the point P, that is omega, but also the water depth, h. In this case, the water depth at the offshore point is HO. As you can see, guess, the script does not know the value of the guess solution. Then we need to define here the guess solution. And a good guess solution can be, in general, the offshore, or better, the deep water solution. Indeed, in deep water condition, the dispersion relationship reads in this way. So we have not the hyperbolic tangent. So a good guess solution is equal to omega squared over G. So the gas solution can be omega times omega over G. In this case, the script should compute the correct value of K. How can we verify if the computed value is correct? We can write the error that format, which is the error. How we can get if the solution, if x star is the solution of this one? Verification. Is x star the solution? This is the question. We need to compute omega squared minus G x star hyperbolic tangent of x star times h, and we need to understand which is the value. We can compute this one, the absolute value, and if we can write this one as epsilon, if epsilon is lower than tolerance, then yes. Otherwise, if is too big, the answer is no. So we need to compute the absolute number, the absolute value of the function. So we can write here the absolute value is np.abs, the function, but we can use this one. We can use this one of the dispersion relationship by using the computed K with omega and with the correct water depth. So now, if I forgot something, this one and this one. If I execute this script, we should read here the error, and if the script is well written, the error should be very small. Error is equal to 0, exactly to 0. We can also, we can also, just for example, try, I decrease the font size here. We can change the water depth, just for example, 20 meters. If I execute again, we wait for a while, and the error is again K. We can try to write also the solution. The solution is K equal dot format K. Actually, this is KO. KO and KO. So you can see the obtained solution. The solution is this one. So this is the value of the solution. If you put this value into the dispersion relationship here, this difference should be more or less equal to 0. Now we have done, if we come back here, we have done also this one. Then we need to compute the wave celerity at the point O. So we go here and we compute CO equal to omega over KO. And we have done also this part. Then we need to solve the dispersion relationship at the point P. So we can simply copy and paste this one. The only thing that we need to change is the water depth. And of course the name of the solution, that is now Kp, the name of the celerity, and then we get also the value of Kp and Cp. Then we can compute the group celerity, and we can make here the group celerity at the point O is equal to the celerity at point O over 2 point dot 0 times 1 plus 2 times KO times HO over NP hyperbolic sine of 2 times KO times HO. And it's enough. This is the group celerity offshore and the group celerity inshore, in which the celerity is Cp, the wave number is Kp, the water depth is Hp, and also here. So we computed this celerity, and then we can compute the Shoaling coefficient. The Shoaling coefficient, Ks, is equal to the square root of the group celerity at the point P over the group celerity at the point O. I don't know if I wrote correctly here. Yes, O over P. And here, no, O over P. Okay? Then we can write also here Shoaling coefficient Ks equal to dot format Ks. Of course, K is equal to radiant over meter. Ks is dimensionless, and we can try to execute the script. If we wait for a while, we should have the Shoaling coefficient that, as you can understand, is equal to 0.97. If we make here 100 of meters and here 2 meters, just to recall the behavior of the Ks. This is Ks, this is H, this is 1. The Ks behavior is more or less something like that. So before we have computed a Shoaling coefficient equal to a little bit lower than 1. So we were in this area. Now we decreased the water depth, then the Shoaling coefficient should be higher than 1. So we can repeat the computation, and we should get a value of the Ks coefficient higher than 1. Indeed, it is higher than 1. If we decrease, so in the first case we were here, now we were here, we are here. Now further decreasing the value of the water depth, we should have a higher value of the shoring coefficient. So we can run again the script, and as you can realize, the KS is increased again. So we are here. If we decrease again 0.3, we perform the computation, and the KS should be increased 1.666 and so on. So now we are here, and so on. So we are computing the value of KS. If we have a higher water depth, more or less equal to the water depth at the point located offshore, we can compute again, and KS should be more or less equal to 1. We can confirm this by looking at the number, and as you can understand, this is more or less equal to 1, of course. So we are somewhere here. Now we have done then up to this point. We have computed also this one. Then we need to solve the Snell law. What I mean when I say that we need to solve the Snell law, we know that C over the sine of beta is constant. But if it is constant, it means that the wave celerity at the offshore point over the sine of the wave direction at the offshore point is equal to the wave celerity at the point P over the sine of the wave direction at the point P. Now, we know this one, we know this one, and also we know the wave direction at the point located offshore. Then the only unknown is this one. So we can write that the sine of beta P is equal to the wave celerity at the point located offshore. The wave celerity at the point located inshore over the wave celerity at the point located offshore times the sine of the wave direction offshore. Then beta P is the arcsine of Cp over Co sine beta 0. So we need simply to write this relationship in our script. So we can write here, compute the wave direction based on the Snell law. Then beta P is equal to the arcsine of Cp, and Cp is this one, so we know the value of Cp, over Co, that is the wave celerity offshore, and we know Co, times the sine of beta O. Beta O we called beta O. So also we can write here beta P. We need to write NP. Pay attention that beta 0 is expressed in degrees, but of course the sine should be applied to an angle expressed in radians. So we need to transform the degrees in radians, and we have this function, degree to radians. Indeed, somewhere here in our presentation, we used no, we can add here deg to rad of something. This function converts an angle expressed in degrees to radians. Of course, we want, it is not necessary, but it is useful to get the value of the wave direction at the point P in degree again. So we use the more or less the same function that convert the radians to deg. So we can copy also this one, and we have another function that is called rad to deg. This function converts an angle expressed in radians to degrees. Okay? Then we can compute also Kr, that is the ratio of the cosine of the two angles of beta O over beta P, but again we need to transform the degree in radians. And P deg to rad. And I guess, okay. Then we can write also the refraction coefficient Kr, and here we write Kr. Now, if we have written correctly the script, we should have both the value of Ks and the value of Kr. Of course, as the wave direction offshore is defined by beta O equal to 0, it means that the waves are propagating perpendicularly to the bathymetric lines. The refraction phenomenon does not occur. Indeed, if we write also the angle wave direction at the point O degrees, and we write here beta O, and also the wave direction at the point P, in this case, we should have both angle equal to 0. Indeed, the offshore angle is equal to 0. Then, oh sorry, I forgot something here. Then the wave angle offshore is 0, and of course the wave angle at the point P is 0, as you can read here. If we change the wave direction offshore up to 30 degrees, we should have that beta P is lower than beta O. As you can guess here, the wave angle is decreasing. Of course, we have at 90 meters, so more or less water depth very similar to the offshore one. If we write here 1 meter, so very close to the shoreline, we should have a wave angle lower than 30 degrees. Indeed, we have 9 degrees. So we can write a kind of sketch. Offshore, we have this wave direction, and then the wave crest is something like that. Here we have the bathymetric line. At the point O, at the point P, the wave angle is decreased down to 9 degrees. Then the wave crest is something like that here, and here is more close to the direction of the bathymetric lines. So during the propagation, the waves tends to become, as you can see, to become parallel to the bathymetric line. So here we have done also this one, we have done this one. The last operation is to compute HP. So we can write here HP equal to H offshore times KS times KR, and that's all. HO is okay, and HP. So, and then we can write here wave height at the point O in meters, and here we can write HO, then we copy at the point P, HP, we execute, and we should have that the wave height is computed at the point P. So we start from 1 meter at the point P. We have a wave height equal to 1.17 and so on. Of course, if the waves are perpendicular to the bathymetric line, the wave height is higher, because the refraction tends to decrease the wave height. So offshore we have 1 meter of wave height. At the point P we have 1.25 meters. Here the water depth is equal to 1. Then it is very likely that this wave is breaking. And that's all.